All right, so this is lecture 9 of linear algebra, and let me begin by reviewing the definition of reduced row echelon form. So let me find the definition that I gave in the notes, which makes it easier to follow, I believe. So we had talked about the augmented matrix of a system. And okay, so first let's review what are the element. Oops, did I start to record? Just double check. Yes. The elementary row operations on a matrix. There are 3. The first is to interchange 2 rows. The second is to multiply a row by a non-zero scalar. And the third is to add or subtract a multiple of one row to a different row, to another row. And so let's just take an example. Suppose I take the matrix A to be 1, 2, 3, 4, 5, 6, 7, 8, 9. If I interchange rows 1 and 2, I get the matrix. The first row becomes the second row. The second row becomes the first row, and the third row doesn't change. So I've interchanged 2 rows. Now, in fact, I can carry that out or see this effect by multiplying the matrix A by a very simple matrix. Suppose I take the matrix, let's see, what should I call it? These are what are called the elementary matrices. And you get an elementary matrix by performing an elementary row operation on the identity matrix. So suppose I take the identity matrix I, 1, 0, 0. This is a 3 by 3 identity. And I interchange the first 2 rows. I'll call this matrix E12 for the moment. So this is the matrix I got by interchanging the first 2 rows of the identity matrix. And let's look and see what happens if I take the matrix A and multiply it on the right by E12. So E12 is 0, 1, 0, 1, 0, 0, 0, 0, 1 times my matrix A. So this is exactly that. So I can perform the elementary row operations, at least the elementary operation of interchanging 2 rows, by multiplying the matrix A on the left by this elementary matrix, which I got by interchanging the corresponding rows on the identity. And in general, suppose we have I is the n by n identity matrix. So this is always a matrix with ones down the main diagonal and zeros everywhere else. And let's say that E, what is the notation that I should use? I'll call it EPQ. So this is the matrix obtained by interchanging rows P and Q in the identity matrix I. And if A is an m by n matrix, then if I multiply EPQ times A, sorry, let me call this not A. And maybe I shouldn't call this P and Q. But let's just keep it n by n. A is an n by n matrix, then EPQ times A is the matrix obtained by interchanging rows P and Q in A. So if I multiply A by this elementary matrix EPQ on the left, it interchanges rows P and Q. What is another elementary? What is the second elementary row operation?
I have a question.
Yes, go ahead.
Can you explain it one more time? What you wrote on the second line?
The second line, right here.
Yes.
So I'm defining a matrix EPQ. So P and Q are integers between 1 and n, different integers. And EPQ is the matrix obtained by interchanging rows P and Q in the matrix I. So for example, if I is the 3 by 3 identity matrix, then E12 is the matrix you get by interchanging rows 1 and 2 in I. So if you interchange rows 1 and 2, you get 0, 1, 0, 1, 0, 0, 0, 0, 1. You got from here to here by taking the first row and making it the second row, and taking the second row and making it the first row, right? So if I interchange the first two rows in the identity matrix, this is what I get. And I'm calling this matrix for the moment E12. And if I multiply E12 by any matrix A, 3 by 3 matrix A, it will interchange the first two rows of the matrix. It will interchange rows 1 and 2. Right, that's what I'm saying. And in general, if you want to interchange rows P and Q of a matrix, you can multiply it on the left by this matrix, this what's so-called elementary matrix, EPQ. So, I mean, this is all, again, written out very explicitly in the text, and you need to spend, I mean, so this is difficult in the beginning, certainly, and you have to put in a lot of time to understand the algebra behind what's going on. The second elementary row operation is multiply a row Say, suppose you want to multiply row K by a scalar C not equal to 0. So suppose you had the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and we take C to be equal to, I don't know, 4. So if you multiply, let's say, the second row by 4, the first row doesn't change, the third row doesn't change, but you multiply every number in this row by 4, you get 16, 20, 24. And you could obtain the same thing by taking the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and multiplying it on the left, not by the identity, this is by the identity, but if you multiply the second row of the identity by 4, you will get this matrix. I multiply the second row by 4, and now if I take this elementary matrix times this matrix, I get exactly this. You can check if you do this matrix multiplication, the first row doesn't change, the third row doesn't change, but the fourth row is multiplied by 4. And finally, the last elementary operation is to add a multiple of one row to another. So suppose I take the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I want to add 2 times row 1 to row 2. So I'm not going to change row 1, and I'm not going to change row 3, but I'm going to take 2 times the first row and add it to the second. I'm adding 2 times row 1 to row 2. If I multiply 1, 2, 3 by 2, I get 2, 4, 6. If I add that to the row 4, 5, 6, I get 6, 9, 12. So I get 6, 9, 12. Right? So I obtain this matrix from this matrix by adding 2 times the first row to the second row. Okay.
I have a question.
Yeah, go ahead.
Can you explain one more time the bottom matrix?
This.
Yeah.
So here I'm starting with the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So the third elementary row operation on a matrix is to add a multiple of one row to another row. So in this example, I'm adding 2 times the first row to the second row. I'm not changing the first row. I'm not changing the third row, but I'm replacing the second row by adding to it 2 times the first row. The first row is 1, 2, 3. If I multiply that row by 2, I get 2, 4, 6. If I add that to the second row, 4, 5, 6, 2, 4, 6, 4, 5, 6, these are the coordinates of row vectors I add, I get 6, 9, 12. So the only change is the second row changed, 4, 5, 6 became 6, 9, 12.
Thank you.
So these are the elementary row operations that we use constantly in linear algebra. And if I took the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and I took the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. In the identity, if I added 2 times the first row to the second, my second row will become 2, 1, 0. And you can check that if I take this elementary matrix and multiply it by the original matrix, I get exactly the same thing. This elementary matrix times A gives me this. So the point is that the so-called elementary matrices, and let me repeat the definition. An elementary matrix is a matrix obtained from the identity matrix I by performing exactly one elementary row operation. Again, you have to remember you have to know what are the elementary row operations. You can interchange two rows. You can multiply a row by a non-zero scalar, or you can add a multiple of one row to another row. And we can express each of these operations by an elementary matrix, right? Now, an m by n matrix doesn't have to be a square matrix. An m by n matrix is in what is called reduced row echelon form if it satisfies the following properties. First, every non-zero row, every zero row, which you can, in a matrix, a row can be all zeros. Every zero row is below every non-zero row. So for example, you have a matrix that looks like this. Maybe the last two rows are all zeros, and so here's a matrix. This happens to be a 4 by 4 matrix. This row has non-zero coordinates. This row is non-zero coordinates. These rows are all zero, and the zero rows are below the non-zero rows. So every zero row is below every non-zero row. That's the first condition. Second, every non-zero row has, as you go from left to the right, has 1 as its first non-zero coordinate. So in the first row, the first non-zero number is a 1. In the second row, the first non-zero number is a 1. That's the second condition. Third, as you move down the matrix from one row to the next, these first non-zero ones, the first ones, move to the right. What that means is here in the first row, here's the first non-zero number, the first 1. In the second row, the first non-zero 1 is to the right of this. It's in a column to the right of the column where this 1 is. This 1 is moving to the right. And above and below every initial 1, that is coordinate 1, which is the first non-zero element on the row, above and below every initial 1, every coordinate is 0. So here's a 1, and below it, there are only zeros. Here's a 1, and above and below it are only zeros, right? You can have a 2 here, a 3 here, it's all fine, but this matrix is now in reduced row echelon form. The non-zero rows are above the 0 rows. Every non-zero row has its first non-zero coordinate equal to 1. As you move from one row down to the next, these initial ones are moving to the right. Could have a matrix that looks like this. One, one, one. In each of these non-zero rows, the first non-zero coordinate is a 1. And as you move from one row to the next, these ones have been moving to the right. So this matrix, and above and below these initial ones, are all zeros. So this is an example of a matrix in reduced row echelon form. Okay. Any questions about this? So these are a whole series of new concepts to understand. Now, elementary matrices and reduced row echelon form matrices come up in many, many, many different contexts. So the first is solving systems of equations. Let me look at one more example of that. We've already done several. Or maybe what is a here's a system of equations. In this case, it's 2 equations and 2 unknowns. So first of all, we have the matrix of coefficients. Which just involves looking at the x's and y's, 9, 11, 5, and 6. But then we augment this matrix. We get the augmented matrix. By adding a column, which is the right-hand sides of these equations. So the augmented matrix is 9, 11, 5, 6. And then I add this column minus 1, 3. Right? I'm just putting this dotted line just to make it sort of clear that I augmented the coefficient matrix by adding the right-hand sides. Now, we saw that there are 3 operations on a system of equations that produce equivalent systems, which are systems with exactly the same solutions. Interchanging equations, multiplying one equation by a non-zero scalar, or adding a multiple of one row to another. Those are exactly the elementary row operations, which we could get by multiplying, if we wanted, by an elementary matrix. And the equivalent of Gaussian elimination, when we're dealing with the matrices associated with the system of equations, is to solve the system by putting the augmented matrix in reduced row echelon form using elementary row operations. So that's what I'm going to do. I want to put this matrix in reduced row echelon form. So the first non-zero number in a row has to be a 1. Here, it's not a 1, it's a 9. So what can I do to make this a 1? I leave the second row the way it is, but I multiply the first row by a 9th. I get 1, 11 over 9, minus 1 over 9. Now I have a 1 here. Underneath that 1, I need to get a 0. So what can I do? I have the first row. And if I take this, if I add minus 5 times the first row to the second, or equivalently, if I subtract 5 times the first row from the second, I end up with a 0 here. See, let me just write down what that means. I have the second row, 5, 6, 3, multiply the first row by 5, I get 5, 55 over 9 minus 5 over 9, and subtract. 5 minus 5 is 0. 6 is 54 over 9, that's minus a 9th. Sorry, it's plus a 9. It's minus 5 times this row plus this row. So for minus 5 times, it's this row minus this row. Sorry. It's 5, 6, 3 minus this row. 6 is 54 over 9, so that's minus 1 over 9. 3 is 27 over 9. 27 minus 5 over 9 is 22 over 9. Is that right? 27 minus 5 is 27, plus 5 is 32 over 9. So this row becomes 0 minus 1/9, 32 over 9. I got from here to here by subtracting 5 times the first row from the second. Okay, now in the second row, I want the first non-zero coordinate to be a 1. So I'm not changing the first row at this point. But if I multiply the second row by minus 9, I get a 1 here. So multiply the second row by minus 9, I get 0, 1, minus 32. Then I want to get a 0 here. So I'm not doing anything to the second row, but I'm going to take the first row minus 11/9 times the second row. So 1 minus 0 is 1. 11/9 minus 11/9 is 0. And what's the number over here? It's minus a 9th minus 11 times minus 32. So 11 times 32 is 352 minus a 9th. Something doesn't look right to me, but let's see. 1 11/9 minus 1/9, 0, 1 minus 32. So 0 and 1 minus 32 doesn't change. I multiply this row, I multiply this row by minus 11 over 9. Minus 11 over 9. Minus 11 over 9 plus 11 over 9 is 0. Minus 11 over 9 minus 32 minus a 9th is 352 over 9 minus 1 over 9, which is 351 over 9. And 9 into 351 goes exactly 39 times. So this system, the system of equations associated with this matrix, is equivalent to the system associated with this matrix. And what does this matrix say? 1 times x plus 0 times y equals 39. 0 times x plus 1 times y equals minus 32, or x equals 39, y equals minus 32. And if you plug those values into the initial system, you'll see this is the solution of the system of equations. Okay.
Professor,
Yeah,
I have
go
a
ahead.
question. How did you get the 0 from the mirror right here? Did you multiply
Which 0 are you talking about?
the last part? The last part right here.
Here?
Yeah. No, the
Okay.
one on top of that.
So do you see how I got this 0?
Yes, I did.
Right? I subtracted 5 times the first row from the second.
Mm-hmm.
And you see how I got this 1? I multiplied the second row by minus 9.
Okay. Mm-hmm.
And how did I get the 0 here?
Mm-hmm.
I subtracted 11/9 times the second row from the first row. 11/9 minus 11/9 is 0. I'm adding minus 11/9 times the second row to the first to convert this coordinate into a 0. Because this is just 11/9 minus 11/9.
Okay.
And the important theorem, which is really an algorithm, is that every matrix is row equivalent to a matrix in reduced row echelon form. That is, if you take any matrix, you can perform elementary row operations to obtain a matrix in reduced row echelon form. And this is really just Gaussian elimination. You can always interchange rows. So whenever you have a 0 row, it's below every non-zero row. And you can find the first column that has a non-zero coordinate and interchange rows, so that's in the first row. And then you can multiply that row by whatever is necessary, so the first non-zero coordinate becomes a 1. And then subtracting multiples of that row from the other non-zero rows gives you a matrix where in the column where the first non-zero entry is a 1, everything beneath it is a 0. And then you do the same thing with the second row and so forth. So you can always put a matrix in reduced row echelon form. And again, I've done a few examples, and there are many more in the notes. Let me say one more thing about matrix multiplication. So in the notes, this is section 2.5. It's called Understanding Matrix Multiplication, which comes down to understanding what happens if you have a matrix and you multiply it on the right by a column vector, or on the left by a row vector. So suppose this is an m by n matrix, A11 up to A1n, AM1 up to AMN. And I take, so this is my matrix A, and I take a column vector x, x1, x2 down to xn. So AX is going to be this matrix times this vector. And this is an m by n matrix times an n by 1 matrix. That's just a column vector. So the result is going to be a column vector, which is m by 1. Let me just call it y1 up to ym. And the question is to understand this. What is this column vector that you get? So when you multiply rows into column, what is y1? Y1 is A11x1 plus A12x2. You're multiplying this row times this column up to A1n xn. Y2, second row, first column, you're multiplying the second row, A21 up to A2n, into this. Y2 is A21 x1 plus A22 x2 up to A2n xn, down to the last coordinate, ym, which is AM1 x1 plus AM2 x2 plus AMN xn. So the vector y1, y2 down to y sub m, this is the first coordinate. This is the second coordinate. All the way down to the last coordinate, the mth. And if you look at this, you can write this as a sum of columns. First column, that's the first column, A11x1, A21x1, down to AM1x1, plus the second column, A12x2, A22x2, AM2x2, all the way up to, it's going to be a sum of n columns. The last one is A1n x1, A2n x2, down to AMN x. This is n. xn, xn, xn. And I can factor x1 out of this first column. This is really x1 times the A11, A21 down to AM1. And I can factor x2 out of this, x2 times A12, A22, AM2, all the way up to x sub n times A1n, A2n, AMN. And what I have here is a linear combination of these A's. And what are these A's? Here is my matrix A. Let me write it down again. A was the matrix A11, A21, down to AM1, A12, A22, down to AM2, A1n, A2n, down to AMN. And in this matrix, this is the first column. This is the second column and so forth. This is the nth column. What this is x1 times the first column of A plus x2 times the second column of A up to xn times the nth column of A. So this is a wonderful explanation of what matrix multiplication does. If you have AX, right? This is an m by n matrix. This is in column vector n by 1. You get a linear combination of the columns of A. You get the first column of A times x1, the second column of A times x2, the third column of A times x3, all the way up to the n, which is the nth column of A times xn. So multiplying a matrix by a column vector on the right gives you a linear combination of the columns. So let's just look at an example. Suppose I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and I multiply that by the vector, I don't know, 4 minus 1, 2. So this is going to be a linear combination of the columns. It's going to be the first column, 1, 4, 7 times 4. The second column, 2, 5, 8 times minus 1. And the third column, 3, 6, 9 by 2. You get this linear combination of the columns of A. And we have an analogous way to understand what happens when you multiply a matrix by a row vector on the left. So let's take a look at that. Suppose I have an m by n matrix, A11, A12 up to A1n, A21, A22 up to A2n, down to AM1, AM2, AMN. So this is my m by n matrix A. And I'm going to multiply that by a row vector, x1, x2, up to x sub n. So what do I get this? So this is a 1 by m matrix. And the result is going to be a 1 by n. It's going to be a row vector with n coordinates. Right? So what is the first coordinate when I do the multiplication? It's this row times this column. I get A11 x1 plus A21 x2 down to AM1 xm. That's the first coordinate. Second coordinate, I multiply this row times this column. I get A12 x1 plus A22 x2 down to AM2 xm. All the way to the nth coordinate, this row into the final column. This is A1n x1 plus A2n x2 up to AMN xm. It's this vector. And I can write that as a sum of m vectors. I can look at the first coordinate, the first number in each coordinate. So I have A11 x1, comma A12 x1 up to A1n x1 plus the second coordinates, that's the row vector A21x2, A22x2, A2nx2, plus all the way up to these last coordinates, AM1xm plus AM2xm plus AMN xm. AM1xm, AM2xm, AMN xm. And then from each of these vectors, like from this first vector, I have an x1 in every coordinate. I can pull that out. This is x1 times A11, A12, up to A1m. Here I have an x2 in every coordinate. I can factor that out. x2, A21, A22, up to A2n. And from the last coordinate, I can factor out xm times AM1, AM2, AMN. But each of these is a row of the original matrix. This is x1 times row 1 of A. This is row 2, x2, row 2 of A, up to xm, row m of A. So what is this? This is a linear combination of the rows of the matrix A. So when I take a matrix and I multiply it on the left by a row vector, I'm taking the linear combination of the rows of the matrix with the scalars that come from x1 up to xm. It's some linear combination of the rows. So multiplying a matrix on the left by a row vector gives me a linear combination of the rows, just as multiplying a matrix on the right by a column vector gives me a linear combination of the columns of the matrix A. So this is an extremely useful way to understand what happens when you multiply a matrix by a vector on the left or the right, and it allows you to understand what goes on when you're doing matrix multiplication, which is just successive multiplications of a matrix by either a row vector or a column vector. It's also useful to introduce one other concept right now. Suppose we have a matrix A. This is an m by n matrix. And this matrix is made up of n columns, first column, second column, up to the nth column. We have n columns. And what is called the column space of A. So each of these columns is in Rm. Each of these has m coordinates. There are m rows, there are m coordinates in each vector. So these are vectors in Rm. The column space of A is the subspace of Rm spanned by the columns of A, which means the set of, or the subspace of all linear combinations of the columns of A. But how do you get a linear combination of the columns of A? It's just AX, if X is any vector, AX is a linear combination of the columns of A. So if you look at all possible linear combinations, that's the set of all vectors of the form AX, where X runs through all the vectors in Rn, right? X is an n-dimensional vector. So the column space of A is the set of all linear combinations of the columns of A, which is exactly the set of all vectors in Rm. This is contained in Rm of the form A times X. You look at all possible products of A with the column vector, and that gives you the column space. And that's a subspace of Rn. Okay, so we're doing a lot today. We spoke already about an invertible matrix. An n by n matrix A is invertible if there exists another n by n matrix B such that A times B and B times A are equal to the n by n identity matrix. So we already saw from homework, if n is equal to 2, and we look at the 2 by 2 matrix A, B, C, D, we saw that this is invertible if and only if a certain number called the determinant of A equal to AD minus BC is not equal to 0. And if the determinant of A, which is AD minus BC, is 1, which is not 0, then if we take the matrix A, B, C, D and multiply it by the matrix D minus B minus CA, or do this in the opposite order, if you do this multiplications, you see you get the identity. So the matrix ABCD, if AD minus BC is 1, certainly has this inverse. This should be ABCD. And why would that? ABCD. So for 2 by 2 matrices, it's easy to know if a matrix has an inverse. You just calculate this number called the determinant. We'll see in a couple of weeks, we'll study determinants in more detail, and we'll define the determinant of an n by n matrix. And exactly the same theorem is true. An n by n matrix is invertible if and only if its determinant is different from 0. But it takes a while to develop the theory of determinants. But what is true always is if A is invertible, its inverse is unique. There is a unique, that means one and only one, matrix B such that AB equals BA is the identity. And let's prove that. So suppose we have matrices B and C, and AB is the identity, and CA is the identity. I claim B is equal to C. Let's see. So B, if you multiply any matrix by the identity, the matrix doesn't change. So B is the same as identity times B. But the identity can be written as C times A. So this is C times A times B. But by the associativity of matrix multiplication, this is C times AB. But AB is the identity. C times the identity, which is C. So B equals C. So this proves that the inverse of a matrix, if a matrix is invertible, it has a unique inverse. In that case, we write the inverse as A to the minus 1. So A to the minus 1 means the inverse of the matrix A if the matrix A is invertible. So the question is, how can we find an inverse? Let's start by noting some algebraic properties of inverses. So B is the inverse of A if AB and BA equal the identity. But this is the same as saying that BA and AB equals the identity, which means A is also the inverse of B. So there's a certain symmetry here. If B is the inverse of A is the inverse of B. So another way of saying that is, if B is equal to A inverse, then B inverse, which is the inverse of A inverse, is A. So we have this property of inverses. It's like, if you take an invertible matrix, if you take its inverse, and then you take the inverse of that, you're back where you started. So like the double inverse of a matrix is the matrix. And a second property of inverse is the following, that A and B be invertible, then A times B is invertible. So the product of invertible matrices is invertible. And what is the inverse of the product AB? It's not the product inverse of A times the inverse of B, but it's the opposite order product. It's B inverse times A inverse. So if you have two invertible matrices and you multiply them, the inverse of AB is the inverse of B times the inverse of A in that order. And the proof is very simple. If I take AB and multiply it by B inverse A inverse, by associativity, that's A times BB inverse times A inverse, right? I haven't changed the order. But BB inverse is the identity. So A inverse is equal to I. So AB times B inverse A inverse is the identity. And in exactly the same way, B inverse A inverse times AB is B inverse times A inverse A times B. This is the identity. B inverse identity B, which is B inverse B, which is I. So we have two basic properties of inverses. The inverse of a matrix is the matrix, and the inverse of the product is the product of the inverses, but in the opposite order. And by induction, if you have a product of n invertible matrices, and you take the inverse of those n matrices, that's the product of the inverses, but in the order reversed. Let's just look at an example of that because it's interesting. So some examples. Suppose A, 1, 2, 3, 4. And B, this is just an example in the book, 2, 5, 3, 7. So the determinant of this matrix is 1 times 4 minus 2 times 3 is minus 2, which is different from 0. So A is invertible. And in fact, A inverse is equal to minus 2 minus 1 minus 3 halves minus a half. Yeah. And for B, the determinant of B is 2 times 7 minus 3 times 5, 14, that's minus 1. And B inverse is going to be minus 7 minus 2 minus 5 minus 3. Oops, sorry, that's not right. It's almost right. Plus 5, 3. This is plus 1 and this is plus 3 halves. I should check just to make sure. If I have 1, 2, 3, 4 times minus 2, 1, 3 halves minus a half, I get minus 2 plus 3 is 1. 1 minus 1 is 0. Minus 6 plus 6 is 0. 3 minus 2 is 1. And if I multiply B times B inverse, 2, 5, 3, 7 times minus 7, 3, 5, minus 2, minus 14 plus 15 is 1. 10 minus 10 is 0. Minus 21 plus 21 is 0. 15 minus 14 is 1. So those are the inverses. And what is A times B? A times B is 1, 2, 3, 4, 2, 5, 3, 7. So this is 2 plus 6 is 8. 5 plus 14 is 19. 6 plus 12 is 18. 15 plus 28, I think, is 43. So that's the product AB. And what is the determinant of AB? It's 8 times 43 minus 18 times 19.
Professor, how did you get the inverses, the A inverse and the B inverse?
Oh, well, we have the rule. This was in the homework and in the text. If A is A, B, C, D, and the determinant of A, AD minus BC, let me call that delta, is not 0, then A inverse is the following matrix. It's D over delta minus B over delta minus C over delta, A over delta. So for 2 by 2 matrices, there's a simple formula for the inverse. So that's how I got the inverses. And eight times 43 is 344. And 18 times 19 is 342. So the difference is 2. So the determinant of AB is 2. So AB inverse is, by this formula, 43 over 2 minus 19 over 2 minus 18 over 2, which is 9, and 8 over 2, which is 4. And it should be, if you multiply this times this, plus 19, let's see, I'm just sort of curious. 4 times 43 minus 9 times 19 does equal 1, yeah. This is the identity. And you can check, what is B inverse A inverse? B inverse is minus 7, 5, 3 minus 2. A inverse is minus 2, 1, 3 halves minus a half. If I multiply this, I get 14 plus 15 over 2 minus 7 minus 5 halves minus 6 minus 3, 3 plus 1. So this is 14, 28, 43 over 2. 7 is 14 minus 19 over 2 minus 9, 4. This and this are exactly the same. So AB inverse equals B inverse A inverse. This is just a numerical example to provide some sort of psychological support for this. Now, there's a nice connection between reduced row echelon matrices and invertible matrices. And you can see it like this. So that A, B, and n by n matrix there exist elementary matrices. Let's say E1, E2, up to maybe E sub k, such that if I take A, multiply it on the right by E1, then by E2, and so forth up to E sub k, I get the matrix R, which is in reduced row echelon form. Now, And inverse matrices are invertible. So let's just say that A is invertible if and only if its reduced row echelon form is the identity. Because if that were the case, if R is the identity, then A times this matrix is the identity, and this is the inverse. So if R is the identity, let's see, R is the identity, A is invertible. But if A is invertible, this matrix R, what does R look like? R is in reduced row echelon form. It's an n by n matrix. If R has any 0 rows, then A cannot be invertible because A would have a 0 row. So if A is invertible, then the reduced row echelon form has no 0 rows. So it has to have a 1 in every row, but there are only n rows. So there has to be a 1 in along the whole main diagonal and zeros everywhere else. So if A is invertible, the reduced row echelon form is equal to the identity. So I'll talk about this more on Wednesday because this really takes a little bit more time. But if you start with the matrix A, you multiply it by elementary matrices to put it in reduced row echelon form. The product of the elementary matrices is going to be the inverse. Let me see if I have a nice example of this. Well, let's just take the simplest example, the one we always use. Suppose I take the matrix 1, 2, 3, 4. So I want to put this in reduced row echelon form. I already have a 1 in the first coordinate of the first row. I want a 0 down here. I can get a 0 here by subtracting 3 times the first row from the second. That means I take this matrix. I'm not doing anything to the first row, but I'm subtracting 3 times the first row from the second. This is minus 3, 1. So if I perform this matrix multiplication, I get 1, 2, 0, minus 2. Then I want to get a 0 here. So I want to multiply the second row by minus a half. 1, 0, 0, minus a half is going to give me 1, 2, 0, 1. And then I want to get a 0 here. So I subtract minus 2 times the second row from the first. So if I multiply this by, I'm not changing the second row, but minus the first row minus 2 times the second. So this is going to be 1 minus 2, 0, 1 times 1, 2, 0, 1. I get 1, 2 minus 2, 0, 1. I get the identity. So this product of elementary matrices should be the identity. What is this product of elementary matrices? Let me compute it. 1 minus 2, 0, 1. 1, 0, 0, minus a half. 1, 0, minus 3, 1. So when I multiply this first two matrices, this is 1, 1, 0, minus a half times 1, 0, minus 3, 1, which is 1 minus 3, 1, 3 halves minus a half. And this has to be A inverse. Did I calculate that before? A inverse. Minus 2, 1, 3/2 minus 1/2. Minus 2, 1, 3/2 minus 1/2. So it's my lucky day that the calculations work out. And wow, so we talked about a lot of different things today. It's all in the chapter on matrices. It's a long chapter and there's a lot about matrices to learn. But the idea of elementary matrices, elementary row operations, putting a matrix in reduced row echelon form, this is all fundamental linear algebra to learn. Any questions about this? I'll post some problem session often office hours for the week. And we can. Okay, everyone. If there are no questions, that is it for this beautiful day. Hope everyone gets a chance to go outside and enjoy it. Bye all.
Thank you.
Thank you.